Howdy AP Chemistry, it's Mr. Russell and we're here to talk about orbital shapes and energies. I'm going to show you a little bit of tricks with the electron configurations. Orbitals have regions of high electron probability and regions of zero electron probability. Areas of zero electron probability are called nodes. So I'll draw one node here and I'll think of it as a point. And then I'll draw another node over here and also think of it as a point. Now if I use a guitar string analogy, this would be the neck of the string and this would be the base of the string down here, and whenever you pluck it, it will vibrate, and it will vibrate like a wave right there. So areas of high probability will have high electron probability here, and then we would have zero electron probability at these nodes. Think of it like a string that's kind of like the same way, because remember that these electrons are thought of as waves, particles and waves. The way we look at it in pictures is if this was half of a core, so this would be half right here, half of the electron shell cut in half, cutting an apple in half, we would find that there would be nodes right here in the middle, these little bitty parts of zero probability. But if we looked at the whole circle, like this one down here, we notice that they kind of cover each other up. So whenever you imagine it, that's what a lot of pictures will look like, is they will look like this. But you got to remember that there are nodes in the middle. Degenerate orbitals are orbitals that are equal in energy. So all three p orbitals are degenerate because they are all equal in energy. All 3d orbitals are all degenerate as well. They all have the same level. The Pauli's exclusion principle, or Pauli's exclusion principle, says that in a given atom, no two electrons can have the same set of 4 quantum numbers. An orbital can only hold 2 electrons, and they must have opposite spins. So remember, N was the energy level, L told you the orbital. It was called the azimuth. This was the quantum magnetic number. And it told you the location of the electron, of which orbital it was, and then m sub s was the spin, either up or down. So it says that you have to have opposite spins, but it also basically says that no two electrons can hold the same place. Now the Aufbau principle comes from the German word Aufbau, which means to build, and it says that electrons enter orbitals at lowest energy first. In its ground state, atoms have electrons in the lowest energy orbitals. The order that the orbitals fill is 1s, 2s, 2p, 3s, and so on. So I'll show you a simpler way to remember this, but basically what that means is all matter, even electrons, even you, likes to exist at its lowest energy level possible. Just like you'd rather be sitting on the couch rather than running around exercising, you like to exist at the lowest energy possible level, so electrons are the same way. You may remember me showing you this earlier, and this is good to just represent, but I kind of think it's a little bit of a crutch, and I wouldn't waste your time trying to draw it on the AP test. But basically what it does is you start from the top, you have the 1s, and then the 2s, and then the 2p, and the 3s, and the 3p, and the 3s. It helps you remember the order, and it's easy to remember, to look up, but there's a couple more tricks to remember. Now the better way to remember it is to try to think of it like this. Now this is the Aufbau principle. We build from the ground up, and remember that you would have an electron here, and you would place them at the lowest energy level possible. And then the next one, it would be here and here. And then we put our p orbitals in. I'm not going to draw all those arrows. And we put here and here, and then we put them right here. Now the big step comes whenever we go from the 3p, we actually have to go to the 4s. Ah, very nice. So this is where the Aufbau principle becomes really important. And this gets tested a lot, is this difference right here, is that 4s comes before 3d. Alright, please remember that. Now, Hund's rule says that all orbitals in a sublevel must be half filled with electrons having parallel spins before any may be completely filled. So what that means is that if we have our orbital diagrams right here, and say this is the 2p, or it could be any p, and we have 3 orbitals right here, we have to fill 1 electron here, and then 1 electron here, and 1 electron here. We have to separate all of them like this. I call this the movie theater rule. You can call it the movie theater. You know how whenever you go to the movie theater and you sit with 6 of your friends, and there are 6 empty seats. Well, the first 3 people are going to sit apart from each other, and then we'll start filling in right here. Or whenever you sit at the movie theater, a lot of, say, 6 guys go there. They don't want to sit next to each other unless they actually have to. So that's the idea. And the electrons don't want to be next to each other unless they have to, because they have similar charges and they will repel each other. So the best way to remember the electron configurations on the test is just to take a look at the 1s, the 2s, and the 2p right here. What happens is the electrons will build just the same way, just from the top down to the bottom. So we'll start here at 1s, and remember that this is the s block. All right, this part right here, these first 2 groups are the s block, and this part over here is going to be the p block. These 6 electrons here, these 6 groups, I apologize, and then this will be the D block. Alright, these 10 groups right here. And then this will be the F block down here. These 14 groups down here. Okay, very nice, very cool, very convenient. So what happens is we start building from the top, and we have 1s, and then we build again from the 2s, and then we come across to the 2p, and then we come across to the 3s, and then we come across to the 3p, and then the 4s, and then 3d. So please remember that right here in this jump, this is the 3d, okay? Even though it's in the 4th period, okay, this is 3d. This will help you keep track. And likewise, whenever we get down here, this is 6s, we will end up, this says 5d, this will be the 4f right here, okay? And this is the 5f. Now, of course, there are 2 exceptions to the Aufbau principle. There are copper and chromium, are two elements that have exceptional electron configurations. And I'll explain why in a second. But copper has a configuration that ends in 4s1, 3d10, instead of 4s2, 3d9. What happened is that 1 electron from the s orbital jumped up to the d orbital. Remember that 4s and 3d are very close on that diagram, so it was easy for that 1 electron to jump up. What it likes to do is it likes to fill that d orbital rather than have a full s orbital right there. So that's what will happen. It's actually more stable that way. Likewise, chromium will have a 4s1 and a 3d5 instead of 4s2, 3d4. That 1 electron jumped up to fill that 5th orbital. So fewer electrons are sharing orbitals, and then electron repulsion is decreased and stability is increased. This is where they are. You'll notice that it is 1, 2, 3, 4. Okay, wait, that's not right. 4, 5, 6, 7, 8, 9, 10. Yes, so that's right. 1, 2, 3, 4. This is the fourth one over, and this is the ninth one over right here. Chromium and copper right here. You don't need to memorize them for the AP test, but if they show it to you, you need to be able to explain why. The orbital notation and orbital diagrams are very helpful to use, and it's where you draw boxes for orbitals, and you need to label them, and then you start drawing arrows for the electrons. So you want to pair up the 1s, and then pair up the 2s, and then pair up the 2p right here. So it helps show the spins, and it's a lot easier to draw. So if they ask you for orbital diagrams, that's what this is looking for. You need to draw opposite arrows to represent the spins. So what element would be here? I'll let you look that up, but its electron configuration is going to be 1s2, because it has the 1s, and there's 2 arrows, so 2 electrons, and then 2s2, and then this would be 2p3. Okay, so look that up, alright? So here's a trickier question. We have this electron configuration at top. Atoms of an element X have the electron configuration shown above. The compound most likely formed with is most likely formed with magnesium. So which one is it? Is it going to be Mg2X, Mgx2, Mg2x3, or Mg3x2? Very interesting. So let's look and let's identify its valence shell. Alright, remember that's going to be the outside shell. So this is the valence shell right here. There are 2 electrons in the s orbital and 3 in the p orbital. So if I draw my boxes, there's the 3s, and then there's the 3p. Okay, 3p, and then I'll draw my boxes there. And then let's draw my arrows. 1, 2, and then 1, 2, 3. Very nice. So there are, let's see, we would have 3 available electrons here. So I bet you its charge is going to be a -3. Ah, very good. So let's see, its oxidation state would probably be a -3. Ah, very good, very good. Because there are 3 available electrons right here. So if I added 3 electrons, it would be a -3. Aha. Now magnesium, its oxidation state is a +2, or 2+. So, and then if I had X with a 3-, if I did the crisscross rule, I would get Mg3x2. Aha! Very nice. So it would be D. Take a second and pause the video and try to work out these problems. Number 6 asks for an impossible electron configuration. Well, if we look at C, there is no 2d orbital, so C is impossible. But also, if we look and we see that we have 2s2, 2p6, 3s2, 3p6, and then we go to 3d3, well, that violates the Aufbau principle because 4s2 needs to be next. So this right here proves that this one is impossible as well. So C and E are impossible. Number 7 asks for the ground state configuration of the atoms of a transition element. Well, that's going to be the d orbitals, and that's going to end in a d orbital, and that would be this one right here, 3d5. So answer number D, or answer letter D, has 3d5, so that 7 is D. the ground state configuration of a negative ion of a halogen. So remember, the halogens are in group 17, but it also says that there is a negative ion, so it has going to have a -1 charge. So if it's in group 17, it's going to have 5p electrons. And so, but if it's going to be heavy 1 electron, it's going to have 6p electrons. So that would be this one right here. It's got a full p shell, 1 heavy electron. So that would be B. And the ground state configuration of a common ion of an alkaline earth element. So alkaline earth elements are group 2, and it says common ion. So common ion is that, well, just its ion. So group 2 normally has a +2. So that means we need to remove 2 negative charges. And so we need to remove 2 electrons. When we do that, we also get B right here. So the answer to number 9 is B. It's a little tricky because I did not say that we had to use every one of them, so or you couldn't use one twice. So those are the answers.